So this video is about decay curves for radioactive nucleus. Before we start, please get your pen and notebook ready. Okay. Let's have some revision of previous important concepts first. Okay, we all know that there are some nucleus which are unstable, and they tend to become more stable, okay, through the emission of high energy particles or electromagnetic radiations. And we call this process as a decay process or transmutation, right? Okay, so if we go back to our previous notes, do you still remember this figure, right? So it's just an illustration for us to understand what happens for an unstable nucleus. Alright? Okay, so they tend to release their energy and through some high energy particles or radiation. Right? We also have learned that there are three major types of nuclear radiations. Still remember what are they? Alright, let's have some revision, right? Okay. So the first type we've learned is alpha particles, right? So for alpha particles, you got two protons, two neutrons, okay, and the charge is 2 plus. Okay, and also we have beta particles, okay, and for beta particles we have beta plus or beta minus, all right? Okay, so that's beta minus. Right? And also we have beta plus. Okay. So this pair, we collectively call them beta particles. Okay. So the first one is alpha particles, right? And we have gamma radiations, all right? Okay, so this gamma radiation, we don't call it gamma particle because it's EM radiation, all right? Okay, so normally we say it's gamma, okay, gamma radiation. Okay, so we understand that those unstable nucleus, they tend to emit alpha, beta, or gamma, and become more stable, all right? So the problem is how fast these decays are for different radioactive nucleus, all right? So there are a few things we need to understand before we start to introduce the main concept of this topic. The third thing is that we need to consider a sample of radionuclide. Sorry. Okay, so so in practice, okay, we can't deal with each individual radionuclide. We will have a mass of radionuclides, okay, they form a sample, all right? So consider there are tens of millions of PO nuclei. PO is polonium, which is unstable, right? And they tend to become more stable by emitting the above radiations particle, all right? Okay, so the third thing you need to know is that some of these radionuclides are going to decay, all right? But you don't know which one is going to decay first. So that's the first nature. So that's two natures. Okay? Okay, the first nature is the process is random. The decay process is random. So that means you don't know which one is going to decay, all right? And also you don't know when a particular radionuclide will become decayed. So we don't know the timing, we don't know which, all right? Okay, and the second thing, although the decay process is random, but the rate of decay is actually a constant. Rate of decay is a constant, okay? So that means, so after a particular time, for example, let's say 0.1 second, there are two out of that many of radionuclides are going to decay, but it might be these two or these two, right? We don't know, but there must be two out of the total going to be decayed, all right? And the time for these two out of the total number of radionuclides getting decayed is a constant, all right? Okay, so that's basically the idea, all right? So that's why we could introduce an idea of what we call the definition of half-life, okay? So when you turn to our page notes of lesson 19, okay, so the first one is the definition, the first part is the definition of half-life, okay? And basically the half-life is of a radionuclide is the time taken for half of the unstable nuclides to undergo decay. Okay, so I'm going to change that statement a little bit. Just give me some time. Okay, do you see any problem of this statement? Yes, so possibly we should have a better wording, more precisely. We should add something here. Sorry, better write this way. Okay, so add a sample. Oh, that's ugly. Right? A sample of radionuclides. Okay, so that means it's a sample, it's a group of radionuclides. Okay, and the half-life of that sample of radionuclides, the time taken for half of the undecayed nuclides to undergo decay. All right, so there are a few things we need to take notice. Time taken, so half-life is a time. Half of the undecayed nuclide, that means 1/2, right? Half. Okay, undecayed nuclides undergo decay. Yeah. So it's about the amount of undecayed nuclides to become decayed during that period of time. Okay, and that period of time is called half-life. All right. So let's have a look of this visualization. Okay. Okay. So I'm going to give you 1 minute to make sense of it. All right. Okay. So this is from your textbook. Okay. So let's see what's the meaning of these circles. Okay, so each circle represents 1 million of PO218 nuclei. Okay, and what's difference between the colors? So there are some blue nuclei, there are some red nuclei. Okay, so the blue nuclei is what we call undecayed nuclei. So this one's undecayed. Undecayed nuclei. All right, and For the red one is decay. Okay. Okay. So from the for the first for the first figure, you see that all nuclides, okay, are blue. That means all nuclides are not decayed, are undecayed, right? But after just after some time, so the time we call after 3.1 minutes. So what's so special about that 3.1 minutes? Okay, so that's the half-life of that's PO218. Okay, so that's 3.1 minutes is one half-life of PO. Okay, so that's number could be anything for different radionuclides. For PO's 3.1 minutes, for others it would be different. But the point here is that you see after one half-life, half of the undecayed nucleus become decayed. You might count the number of reds against the total number of nuclei. You see half of them becomes red. That means they are decayed. And you see the the location of these decayed nuclei, they are random. All right. So, like we have said, the process is random. That means you don't know which one is going to be decayed, but you know some of them must be decayed after one half-life, and the percentage of that many of decayed nuclides will be half of the total number of sample in the sample. All right. And how about after another half-life? And after another half-life, you see there are more red against the blue. All right, that means more blues becomes red. But how many of them? Okay, so if you count the number of nuclides as one circle represent 1 million. Okay, so in the beginning, there are 1 million. All right, and after one half-life, it becomes 15 million. Okay, 15 million of what? Of the blue nuclide. That means undecayed nuclide. And after another half-life, it becomes 25 million. Okay, that means another 50% decay. All right. So that means the number of blue nuclide becomes less and less, and after each half-life, you lose half of the remaining. All right. So that would be the idea of half-life. Okay. I give you another illustration in my notes. Okay. So this one is possibly a more geometrical one. Too big. Okay, for this illustration, it gives you the same idea, but this time I use mass instead of total number. Okay, but they are the same, are they? Because you know, if the number of undecayed nuclides become less, that means the mass of undecayed nuclides will decrease proportionally, right? So in the beginning, there are 4 grams of undecayed substance. So let's say if I use blue color again to represent the total undecayed nucleic substance. And after one half-life, half of them becomes decayed, all right? So that means there's another half which is not decayed, okay? And after another half-life, okay, that's 2 grams becomes 1 gram, okay? Okay, so remember the blue region is what we call undecayed nuclides, and gray region, that means the decayed nuclides. Okay, so again we can see the mass of the undecayed substance becomes less and less, and all right, and the decayed substance becomes more and more in the process. Okay, so that's basically the idea of half-life. All right. Okay, so let's go back to see our definition. All right. So for our definition, we see that the half-life of the sample of radionuclides is accounting for half of the undecayed nuclides. So half of the undecayed nuclide, that means the number, and this half could represent a lot of things. Okay, so this half can be on number of undecayed nuclides, right? Number of undecayed nuclides. Okay, and it could be mass of the undecayed nuclides. Mass of, it could be percentage of undecayed nuclides, and it also could be the activity of the sample, right? Okay, could be the activity of the sample. Okay, so possibly I need to explain this a little bit more. So why activity of the samples also would be halved, all right? So activity means a number of radiation emit per unit time, okay? So when you get less and less undecayed nuclides, that means the number of the number of radiation will drop as well, all right? Okay, so we know that activity is also directly proportional to the number of undecayed nuclides. Okay, so in the examination, if they ask you to apply your understanding of half-life, they could ask you to apply it to the number of undecayed nuclides, could be for the mass of undecayed nuclides, could be for the percentage of the undecayed nuclides, and also could be the activity of the sample. Sorry, I should write the sample instead. Sample. Okay. Okay, so we have the definition. We have had the definition of half-life, and also we have some visualization. But how about if we use a graphical way to represent the decay process, then what happens? All right, so if you go to your notes, okay, so here's the first graph, right? Okay, have a look of this graph. Okay. This is what we call a decay graph, right? Decay curve, sorry. And for this decay curve, all right, you need to look at the y-axis first. So what do we mean by n? This n means number. Number of what? It means number of radionuclides. Okay, radionuclide just means undecayed. Undecayed nuclide, number of radionuclide, okay, in a sample, okay, in a particular sample, all right? Okay, so that number is going to drop over the time, okay? And you see after each half-life, okay, so the axis is time, okay? So what's the unit of this time? It could be anything, okay? So the units for some of the half-life, because they drop very quickly, and so for some of the decay curve, unit could be second, or it could be days, it could be year. Okay, so as long as it's a unit of time and it's in proper scale, then you'll be okay. So generally, on the time axis, we will see there's some equally separate half-life. Okay, so for example, T1/2, that means the first half-life, that means the second half-life. All right, that means the third half-life. Okay, and as your number of undecayed nuclides is dropping, all right, so you see after one half-life, okay, after one half-life, how many undecayed nuclides left? Okay, it's half of the original total, right? So divide by 2, all right? Okay, so how about another half-life? After another half-life, you see it's another half, but that another half is not of the original amount of radionuclides, otherwise it would become 0, right? So the original amounts n naught, but now after one half-life, what remains is n naught divided by 2. Okay, so for another half-life, what happened is, okay, you decrease by another half, all right? Decrease by another half. So that means you multiply that number by half. So is the half of the remaining half, right? So the idea is the half of the remaining half. So the half of one half is 1/4, isn't it? All right. So that means after another half-life, it becomes 1/4. So how about after another half-life? Okay. So you see, it becomes 1/8, right? Why? Because that half-life is of the quarter of undecayed nuclides. It's not of the original and not is of the quarter of and not. So it becomes 1/8. Okay, so you see always times 1/2. Okay, so that basically you can see the graph, how graph goes. You're always declining. Okay, and this kind of decline, that means after each period, fixed period of time, the percentage of drop is always constant. And this kind of decay, sometimes mathematically we call exponential decay. Exponential decay. Okay. So that would be the idea. All right. Okay. So that's the mathematical way to see the things. Okay. So, but still remember that for half-life, not only we can see the number of undecayed nuclides, we can also see the mass of undecayed nuclide, or percentage of it, or activity of the sample, right? So that's why I give you another graph in my notes. So here's another graph. Okay, so for another graph, the y-axis is called correct current rate. Okay, we haven't studied this yet, but I just can replace this idea with an equivalence idea, which is what we call, which is directly proportional to the activity of the sample. Okay, remember that activity of the sample is directly proportional to what? To number of undecayed nuclides. Alright? Okay? So that means when the number of undecayed nuclides is dropping, the activity is also dropping, and also they follow the same exponential decay curve. Alright? So that's why you can see the shape of the curve is the same, and also the drop after each time interval will be the same. Alright? The percentage of the drop is always 50% uh, from the amount's one half life earlier. Okay? Right, okay, before we go to the mathematical rule, I need to introduce to you how could we compare different half-life. Okay, so the idea is different radionuclide have different half-life. Okay, and in the graph, in your notes, there's a comparison different half-lives. Okay, again, the y-axis number of undecayed nuclei. Okay, and the x-axis is the time uh, in the units of hours. Okay, so you see they compare. All right, so how many types? There are 4 types. Okay, nitrogen, fluorine, vanadium, and cobalt. Okay, so you see the shorter the half-life, For example, the first one, the half-life is just 9.97 minutes, and you see the drop is quite steep, right? And that's 1.83 hours, 6 hours, and around 5.5 years. Okay, so you see when the half-life is small, the decay curve drops quite sharply. All right, and so when you see really large half-life, you can see that's the curve, the green one. Practically, there's no dropping because the time axis is hours, and the half-life is in terms of years. Okay, so that means for a very long half-life, okay, um, the activity of that sample will remain quite steady for a very long time. Okay. On the other hand, if your half-life is really small and the activity of that sample will drop quite dramatically, right? Okay, so that will be the idea, right, from what we have seen from the graph. Okay, so let's see. Okay, so the conclusion is for long half-life, regular half-life. The sample is state. Okay. For short half-life, decrease is rate. More fastest. Okay, so that would be the idea. All right. Okay. Okay. Now you could have a few minutes break. Coming back, we are going to do some examples in our book, in our notes. All right. So I need to take a break. Okay, we'll continue our lesson. All right. Okay. So remember the definition of the half-life. Okay. Is the time taken for half of the nucleus to undergo decay, right? And okay, so let's see the notes. Okay, so there's the page on page 2. Okay, so here's an example about the definition of half-life. Okay. Right, so which of the following descriptions about the half-life radioactive substance is correct? Okay, A is equal to half of the time for all the radioactive nuclide of the substance to decay. All right, so is that correct? Okay, so the key is here, all the half of the time. So half of the time is good, but how about all the radioactive nuclides? Okay, so if half-life is half the time for all the radioactive nuclide to decay, that means in 2 half-lives, all radioactive nuclide will be gone, right? Is that the case? No. Because when we look back to our graph, okay, so let's see, okay, so this is the what we call decay curve. So when something's decreased each time by 50% of the amount one half-life earlier, so that means you are going to see n naught, half n naught, a quarter n naught, and 1/8 n naught, and the next one 1/16, right? So if that sequence goes on, you see that it becomes smaller and smaller, but it will never zero. In terms of the curve, you could see that the curve approaches zero, but it will never touch zero. Okay, it just goes on forever. Okay, it will never become zero. Okay, so how about the curve here? You see, okay, is it zero? You see zero here. You might say yes, but this zero means practically the activity dropped to zero. But since the scale of the curve is like this, theoretically there will still be very few radionuclides there, but we can't just observe it on the curve when your half-life is too short. All right? Okay, so that means even though sometimes we might see the curve, they come very, very close to zero, or even when you draw it, it touches zero axis. That's just because we can't draw it so accurately. Okay? And that's why theoretically there won't be a time that all radioactive nuclide will decay. All right, B, it is equal half of the time for a radioactive nuclide for the substance to decay. Okay, the problem here, a radioactive nuclide. Okay, it's not about a radioactive nuclide, it's about a group of radioactive nuclei. Okay, that means all the radioactive nucleus in a sample. All right, so that means half of the time for it means the time for half of the radioactive nuclei in a sample to decay. So that's why this one is also wrong. Okay, it's equal to the time for the substance reduce its mass. Okay, all right, reduce it by half. Okay, for the substance, when you see the substance, what's the substance? It's not well defined. It could be the sample, right? It could be the sample, all right? It could be all the substance in the sample to reduce its mass by half. Okay, so we know that the number of radioactive nuclides is going to be reduced by half, but how about the mass of the sample? Okay, the mass of the sample. The mass of the sample is actually not changed. Okay, let me show you the graph here. Okay, so see, okay, still remember this illustration? So that totally, there are group of undecayed nuclides in blue color, right? So after half-life, there are more red color, that means decayed nuclei. Okay, and there are more and more after that, but they are still in the sample. Okay, so that's the key. They are still in the sample. So that means the total number of nuclides actually remains unchanged, even though the portion of radioactive ones becomes less and less. All right. Okay. So for the sample, the mass would be the same. It won't be reduced by half, right? It is equal to the time for the half of the radionuclide to substance. Okay, half of the, okay, so this one must be correct, right? Half of the radioactive nuclide. Okay, so it clearly defines it's about radioactive nuclide, not all the nuclide. It's about the radioactive nuclide. Okay, so half of it to become decayed. All right, so that's why the answer would be D. Alright, so let's have a look at another example. So this one is about the radioactive curve. This is on page 5. Alright. Okay, so spend 1 minute to read the question now. Okay, so this graph is about activity, alright? And what do we mean by activity? Activity means number of decays per unit time. So unit time could be per minute, could be per hour, could be per second. These times per minute. Okay? Alright, and the axis, time axis is in terms of number of days. Okay, that's okay because activity means number of decays per unit time, and on the x-axis, okay, it's about how fast, what the time scale should be used. Since the half-life is in the scale of days, so that means the horizontal axis we use the units of days, right? Okay, so as we can see, the activity will drop over time. Okay, and so question A is about identify the activity of the sample at the start of the measurement. Okay, so what's the activity at the start of the measurement? Should be this one, right? Okay, should be 80. All right. Okay, so we just write 80, but you need to be a bit careful about the units. The units is decays per minute. All right, so you can write decays per minute. Okay, deduce if the activity of the sample even reaches 0. Okay, so you need to determine whether the activity of the sample reaches 0. Is that possible? Become 0? Like what we have said, it's impossible to reach 0. Although it approaches 0 indefinitely, that doesn't mean it reaches 0, right? So no. Okay, determine the activity of the sample after 10 days. Okay, determine activity 10 days. All right, so how could we know about 10 days? All right, it's here. Okay, when you draw a line over here, what number is it? It's less than 5, so around 2 or 3 decays per minute. But can we do more? Can we be so sure about this? Of course, if you just look at the graph, okay, you can only approximate. Okay, so you say approximately, it should be around 2 or 3, right? 2 decays per minute. Okay, so the last part is about the half-life. Determine the half-life of that's MP238. So how could we know the half-life? Okay, so half-life means you first look at the initial level of activity. So you start from here. So that's the initial activity, right? And you look for half of it. Okay, so when we multiply, that's 80 by half, you get 40, right? So you are looking for this one. Okay, so basically it goes from 80 to 40 by multiply by half. Okay, so after one half-life, the level of activity should be around 40. Okay, so draw a line here. Okay, possibly I use another color. It's a thing. Okay. Okay, when you look more closely, is a bit greater than 2. Okay. All right, and so what's the time is it? Should be 2. Okay, should be 2.1 or 2.2. All right, it's up to you, right? So for me, it looks like more like a 2.2. All right, so it takes, we can only write approximately 2.2 days. Okay. Okay, before we move on, can you turn to page 6 and try to do it by yourself? Okay. You can pause the video now and spend some time working on this one to see if you really understand our previous example. Okay, let's track the answers, right? Okay. Okay, first determine the initial number, total number of gold 195 nuclei present. Okay, so initial total number. So the y-axis is the number of gold nuclei. Alright, so it should be here. So that would be the initial level. It's around 27, but it's not 27 nuclei. You see the units here, billions. Okay, so it's approximately 27 billion. Okay, so identify when the number of nuclei fall to 10% of its initial value. Okay, so initial value 27, so 10% of 27 becomes 2.7 billion. Okay, where's 2.7? It's about here, so it's less than 3 a little bit. So let's just yeah, I think it should be very close, right? So if that's 2.7, okay, so oh, sorry, 2.7 should be less than that. All right, so it's a little bit. It's very hard to draw. Yeah, I think this here is close. Alright, so it should be, so because that's when, that means you need to give a time for your answer. So the time is here, so it should be approximately around 650. What's the unit? Days, right? Okay, determine the half-life. So what's the half-life? Okay, so initial level is 27 billion. For the half-life, you need to calculate 27 times 1/2, 13.5 billion. Right, so 13.5, so let's see if that's 12. So 13 should be here, 13.5 should be here, right? Yep, so I draw this one. Yeah, should be around, let's say, 180 days. Number of nuclei remaining after 3 half-lives. Okay, 3 half-lives. What do we mean by 3 half-life? Okay, so 180 days is 1 half-life. So after 3 half-life, it becomes 540 days. Okay, so that's 540 is around here. Okay, that's close, right? Okay, so this should be 2.4, 2.2. I mean, should be 3. 3.6 possibly. Yeah. Okay. Okay, later on we have method, more accurate method to track it. Right, so that's how we can use the decay curve to find our number of undecayed nuclide, or the time for certain amount of undecayed nuclide remains in the sample. Okay. Okay, so do you see any drawback of this method? Sometimes you have to do the approximation because the lines you draw are not exact at where the measurement should be, right? So all these numbers are approximation, but can we have some way to do it more accurately? Yes, we can. So that's what we are going to do. We're going to use a mathematical formula. Okay, so here's the mathematical formula. Okay, let's copy it. So that's the mathematical rule for the half-life. So is this one? Okay, so for this one, n is the number of radioactive nuclide remaining, and n naught is the initial number. Okay, so we need to emphasize n's the number of radioactive nuclide. That means undecayed. That means undecayed. Or it could be the mass of undecayed nuclide, right? And n naught is the initial number. Okay, so that means the number of undecayed at the beginning, and the number of half-lives. Okay. Okay. And the number of half-lives. Okay. So be careful. N's not the time. It's number of half-lives. Okay. It's a number. It's an integer. No, it could be an integer. It could be a decimal, but it's a number of half-lives. Right. Okay, so let's see what happens if we apply this formula. Like I give you a very quick example, okay, to see how could we apply this formula. Okay, so so that's page 7. If you see, that's one example about the activity. And of course, when we see activity, we know that activity just directly proportional to the number of undecayed nuclide. So that means we could generalize this formula. If we use activity, you might just change the symbols a little bit to change it into this way. So instead of use n, you might use a, so that a means activity. And of course, a lot means initial activity. So they are essentially the same, but you use different symbols to start with. All right. The initial activity is 2,000 disintegration per second. So this word in disintegration just means decay. Alright, so that means number of decays per second. After 4 hours, the activity drops to 125 disintegration per second. Find the half-life of the isotopes. Okay? You need to find the half-life. Okay? So, from 2000 to 125 disintegration per second. How many half-life? Okay, so if you use the previous formula, what can you see? All right, so that's 2000 would be our A, okay, per second. Okay, so I would say decay per second, right? I just write per second would be fine. And so that's A log, that's the initial level. And it dropped to 1 to 5, so that's the activity now. Okay, and the time taken is 4 hours, but we need to find the half-life. How long is the half-life? Okay, let's apply the formula. So the formula tells us like this. Okay, so A is 1 to 5. Okay. Okay, you should know how to do it, right? So of course we don't know n, but you could just divide that 2000 to the left hand side. And now when you use 125 divided by 2000, that's 1 over 8. True. Okay, so what n shall I put in to make it 1 over 8? Of course, you can try n equal to 1 is 1/2, and you could choose 1/4, right? So that n equal to 3, all right? Okay, so that means it takes 3 half-lives. So that's how long it takes. It takes 3 half-lives. Okay, but the total time is 4 hours. Okay, so that means 4 hours equals 3 half-life. So half-life, we use this symbol. Okay, so how about 1 half-life? Okay, 1 half-life equals 4 over 3 hours, right? So how long is 4 over 3 hours? In the multiple choice, the units are minutes. So let's change it to minutes times 60 minutes. Okay, so it will give you 80 minutes, right? So the half-life is 80 minutes. Okay, that's how it goes. So that's why we could calculate the length of half-life. So remember, when you use this formula, is what we call exponential equation. The unknown is the index, so you need to be a bit careful how to find that n. A better way to do it, just you try to substitute the integers into n to see if you can get that number. Okay, for most of the question in physics, we don't require you to use very advanced algebraic techniques. So possibly you just substitute integers into n, you will get your answers, right? Okay, that's all right. So let me just give you some time. Okay, so if you want to copy it, you can pause the video to copy it now. Right. Okay, so like what I have said, sometimes it would be better to use this mathematical formula if you need some more accurate answers. Okay, let's see when we go back to our previous example. Okay, so for this example, we suffer some the scale of the graph. That means you see those lines, the red line, or the green and the blue lines. They all end up in the place where we are not 100% sure about the numbers. But now, can we use the formula to help us to find our more accurate values? Okay, so for example, for the last one, determine the number of nuclei remaining after 3 half-lives. Okay, So if we are going to do it in a mathematical way, if we try to do it using math rule, what we're going to do is about the number of undecayed nuclei. So I'm going to use this formula. Okay. After 3 half-lives. Okay, so we know that n naught is 27 billion. After 3 half-life is 3, right? Okay, so we're going to find n, right? So let's try to do some calculation. It's 1 over 8. Okay, so you see the answer will be 3.375 billion. Okay, so when you compare this one to the one we find from reading the graph, you see, okay, there's some errors here due to the limitation of our drawing. Okay, so when we look at the graph, it really looks like 3.6, and possibly our graph is not drawn accurately enough, or when I draw this blue line, it's not exactly the 3 half-lives, right? Okay, but if we use this formula, you get a very much accurate values. Okay, so that's why sometimes we need to use this mathematical rule. Okay, so let's do more by using the mathematical rule. Okay, so I give you 1 minute to read the question and try to apply that formula by yourself. All right. Okay, so first of all, let's see, contains 8 times 10 to the power 12 nuclei. So what's the meaning of this number? So this number is what we call n naught. It's the number of undecayed nuclides. Okay, and the half-life is 24 days, right? Calculate how many thorium-234 nuclei will remaining in the sample. Okay, so you need to calculate how many. Okay, after 120 days. Okay, so let's think if we use the formula, what we are going to use is this formula. N means how many left behind as undecayed nuclides. And 0 means initial number of undecayed nuclides. 1/2 means because you need to apply the half-life each time you halve it, right? So that's lowercase n means number of half-life. Let me emphasize this n. Okay, so this lowercase n means number of half-lives, number of 1t 1/2, right? Okay, so how could we find that n in this case? Okay, so number of half-life means number of days divided by each half-life, right? So that means number of, so it should be total time taken divided by each half-life. Think about this, right? Total time taken is the total amount of time divided by the half-life, the time of half-life. That means number of half-life. Does it make sense? Okay, so in this case, total time taken is 120 days divided by 24. Okay, so both are days. Okay, so there are 5 half-lives. Okay, right? So we now know that there are 5 half-lives. Okay, so now we could substitute in the numbers. Okay, so that basically 1/32. All right. Okay, if you use your calculator properly, you will get this answer. So that's number of undecayed nuclides after 120 days. Okay, right? Okay, possibly need some time to copy it. Okay. Okay, so I'm going to give you a few minutes to work on this. Okay, and after we resume the video, you need to um, you need to check your answer against mine. All right? Okay. Okay, here's the answer. Right? So basically, just apply very similar process for this question, like the one we have just done before. Right? Okay. So the answer would be that's 39 million and 62,500, right? But of course, you need to simplify this because the numbers in the question correct to two significant figures, so you better run off to 3.9 times 10 to the power 7. Okay, so that's number of radioactive nuclides remains remaining in the sample after 150 hours. Okay, good. Okay, here's another example, right? In this example, you see they give you, okay, it's 0.1309 kilogram sample radioactive isotope. Okay, so that's the mass. Okay, so if you see the unit, that's the mass. All right. So it's a bit different than the one we've just done before, right? Okay, so we'll give you some time to read the question within 1 minute. Okay, so for this one, we might need to change our formula a little bit. Okay, so we have formula like this. We use N, and we might use A. There's another possibility that we might use mass as well. Okay, they're all the same. Okay, so that means the mass of the radioactive nuclides in the sample, right? Okay. Okay, so that's the initial mass of the sample. Alright, so that's for iodine-131, which is a radioactive nuclide. Okay, 41 days. Okay, so is that half-life? No, we don't know the half-life, because half-life you are going to find out. Alright, so that's just the time taken. Okay, you will find that's the only. Okay, so that would be the mass remaining. So that would be the mass of remaining undecayed radio isotopes. Okay. Okay, so what's the formula about? We're going to use formula like this. Okay, so there will be our formula, right? Okay, so what's the mass m? So the mass m should be this one. What's sorry, m naught, I mean the initial mass. What would be our mass of the remaining isotope? Of course, the smaller one, right? But remember, if you look close enough, they have different units, so you need to convert them, all right? And there's another mass. If the mass of one nucleus or iodine is this one, so this is quite tricky. Are we going to use this one? Not necessarily, okay? So because that's just the mass of one nucleus, it's not about the total mass of the undecayed nucleus or the total mass of the initial number of undecayed nucleus. So that's just for one particular nucleus, you got the mass. Okay, so we're not going to use this one. But why they give you this number is because the book use another method, so which I'm not going to follow. Okay, so I'm going to use a method which does not need you to use that mass of one nucleus. Okay, so again, do we have enough information? Let me plug the numbers into our formula. Okay, so that mass is 4.01 gram. Okay, and m naught is 0.1300. But wait a minute, that's kilogram. So that means you need to multiply by 1,000. Right, so so it becomes interesting, right? Okay, so again, we're going to divide that number by this number. Okay. Oh, sorry. This should be. All right. Okay. Let's do the division on the left-hand side. Okay. So if you see this number is kind of very close to this one. Okay, so how could we find that's n? All right. Okay, so let's try. So if that's n equal to 1, of course we know this one 0.5. If that's 2, 0.25. Okay, if that's 3, okay, that's 3 becomes 0.125. About 4. Okay, so that's 4, just becomes 0.0625. It's very close. Okay, if it gets 5, becomes 0.03125. Okay, bingo. Here's the number. So that means n equals 5. Okay, of course, some of you might have learned how to solve it by using exponential equation or logarithm. That's okay, but I just need to take care of the general audience that they might not have learned. That's the skills of exponential equation and also the logarithm. Okay, so n equals 5. That okay. So n equals 5. What's the meaning of this one? So that means there are 5 half-lives. 5 half-lives. Okay. So 5 half-lives. How about the length of one half-life? So what's the time taken? That's 41 days. Okay, so that means 41 days equals 5 half-lives. Okay, so that means 5 half-lives equals 41 days, right? 41 days. Okay, so how about each half-life? It's about 41 divided by 5, 8.202 days. Alright, okay, so that's the half-life. Okay, good. Okay, so that means we could apply this method to we can change that formula for the question using mass instead of number of nuclei or the activity. Alright, okay, so let's go to our the last one. Okay, I'm going to give you some time, of course. After you finish, we are going to check the answer, right? Okay, so so you see that we use the formula for mass again. Okay, so 8.9 grams should be the initial mass, and that's 0.556 gram would be the mass after a certain time. Okay, and so you are going to find the half-life. So first of all, you use the formula to find how many half-lives. Alright, okay, and so you apply the formula like what we have done before, and you find out that 0.0625 equals 1/2 to power n, and use our previous method. You see that's when n equal to 4, 1/2 to power 4 equals 0.0625, so that n equals 4. Alright, so that means there are 4 half-lives. But how long does it take for that 4 half-lives? Okay, so you need to find the time taken. So time taken from 12 p.m. on Monday to 36 minutes past 11 p.m. on Thursday. So that means 3 days, but less 24 minutes. Alright, so because for 3 days you are going from 12 p.m. on Monday to 12 p.m. on Thursday, right? But it's not exactly 12 p.m. on Thursday, it's 24 minutes earlier than that, so that means you need to take away 24 minutes. Okay, because the question asks you to determine the half-life in hours, so you have to change all these things into hours. 3 days means 3 times 24 hours, and 24 minutes means 24 divided by 16 minutes hour, right? Okay, so that gives you 71.6 hours. All right, okay, so that's equivalent to 4 half-lives, so each half-life 70.9 hours. If you get the answer, congratulations, you really understand how to do it. Okay, and yeah, I think that's the end of this topic. And for your homework, you might try to do some key questions on the following page. Okay, and of course, as always, we have the answers after the notes. You can have a look to try to see if you really understand the content. Okay, if you have any question, you can leave your message in the collaboration area in the OneNotes. Okay, that's for today. Thanks for watching. Bye.